Let's get started. Hi, everybody. Good morning or good afternoon, wherever you are. Thank you for joining us for another session of EI Live K-12, a session for students, educators, and general audiences. This is a series that is part of the Columbia Climate School. My name is Cassie, and I'll be facilitating the session today. If you're joining us for the first time or are unfamiliar with the Climate School, we are a newly established school at Columbia University, and we're focused on transdisciplinary climate research. The core mission of the school is to develop and inspire solutions and educate future leaders about just and proper societies for a healthy planet. The Climate School is actually the first new school at Columbia in over 25 years, and it incorporates and has integrated the entirety of the Earth Institute, which is the research organization that started the EI Live K-12 series. And this includes Lamont Doherty Earth Observatory, which is the largest scientific research unit that was part of the Earth Institute and now is part of the Climate School. And the school is made up of now thousands of individuals who collaborate across many departments at the university. So what we're hoping to do with these EI Live K-12 sessions is just introduce all of you to our interdisciplinary work through our scientific experts. These are bi-weekly sessions that are taking place in the fall, and they'll continue in the winter, spring semesters as well, also on a bi-weekly basis. And if you'd like any information about those additional events, please do not hesitate to reach out to us. Each week or each session will focus on a specific topic. It'll be directed towards a certain age range. So today we are very lucky to have Dr. Jonny Kingslake, assistant professor in the Department of Earth and Environmental Sciences at Columbia, as well as Lamont Doherty Earth Observatory. Jonny's field, so he's a glaciologist, and he studies ice sheets, and he has done extensive research in this field. And today he's going to specifically discuss how ice flows. And so he's going to be using a little bit of math and physics, and not to totally overwhelm us. And we'll share a recording of the session after we are done. If you do have any questions during the session, please use the Q&A box. And we will also have a guest from NASA's Goddard Institute of Space Studies to share a couple of NASA resources with us after Jonny is done. So Jonny, whenever you're ready, take it away.
Thanks, Cassie. Hi, everyone, and thanks for coming along and being interested in the science and education that we do at the Climate School, and the education specifically that Cassie arranges is fantastic. So I always try to join in with these EI live sessions. So as Cassie said, I'm a glaciologist, and I study all aspects of glaciology, and glaciology is all to do with snow and ice. It's all about the parts of the planet where water is mostly frozen, and so a large part of that is concerned with these large things called ice sheets, which I've got two pictures of here. One's the Antarctic ice sheet on the left-hand side, this big white thing covering the South Pole of our planet, and then this other slightly more abstract representation of an ice sheet. It's actually like a slice through the ice sheet. It's showing the upper surface where, you know, this is air, and then this is ice underneath that upper surface, and all the way through to bedrock beneath, rock beneath. So, and this is a slice through the Greenland ice sheet. But yeah, before I get that to all of this, as Cassie said, this is all about a particular thing called ice flow. Ice flowing like a fluid, like a river or like a syrup or honey, and a little bit of maths and physics as well, because I wanted to give you a taste of how we use simple math and physics to understand all sorts of things about geoscience. And in my case, it's often about ice flow. But I know there's probably a big range of ages and experiences on the call, so I'm sure all of you can get something out of this presentation at different stages. So I'll get started. This is picture of our planet here with a big star showing New York. And actually, I'm going to take you over to one of my favorite apps, which is Google Earth. So this is a big virtual globe, And if you've never played around with this, and if you're at all interested in the Earth and geosciences, really have a look at this, search Google Earth online, and you'll find it really quickly. And it's a big virtual globe, and it allows you to explore the planet and zoom into all sorts of places. Zoom into where you grew up, your street where you grew up, or more relevant for this talk, to parts of the planet which are very different than the ones we're used to, where interesting geology is happening. So straight away, we can see lots of variations in color on this image. We've got green for forest and vegetation, we've got yellowy oranges for deserts. And in a few patches, there's white. There's this white for, well, snow and ice. There's a big patch here. This is the Greenland ice sheet up in the Northern Hemisphere. Can quickly scroll around to the bottom half of the bottom end of the planet. And here's Antarctica again, which we saw in our first slide. And in fact, there's little patches of white on every continent. I'm going to zoom into a place that I went to once as a student on a backpacking trip, and this is the French Alps, this is just the Alps in general, and it goes through Switzerland, France, Germany, and Italy. And I'm going to show one particular place in the French Alps, and this is called the Mont Blanc Massif. Mont Blanc is the largest mountain or the highest mountain in the Alps, and this is the Massif, or like area of mountains which contains Mont Blanc. What's really cool about Google Earth is you can zoom into places and then look at things from an angle. So look at it as if you were flying a helicopter, and you can look at it all in 3D. Now, you might see where I'm going with this. There are these features up in these mountains called glaciers, which is the topic of this talk. These are big volumes of ice which have accumulated up in high elevations. All these white areas at the top are where basically it snows in the winter, just like it does in many other parts of the planet. But in the summer, it never gets warm enough to completely melt away that snow. You know, like in our climate, in most of the places where it snows, in the summer, or in fact, usually pretty quickly after it snowed, all of that snow is removed because the weather gets warm enough again and it just melts away. But if you go up to the tops of mountains where it's colder, or to the North Pole or South Pole where it's colder, you can find places on the planet where it never gets warm enough to melt. And that snow just builds up and up and up and up. And that's all these white patches, these high elevation patches. This is snow which never melts, or if it melts a little bit, but it is never completely removed. And these are the parts of glaciers where snow is accumulating. So that kind of makes sense, right? It's just that the climate up there is cold enough that it never melts. Now, the reason I'm really wanted to show you Google Earth, and I'm going to use the fact that you can look at things from the side, is that actually the ice, yes, we can see the snow up here, but this is actually ice all the way down this valley. This is called the Mer de Glace. It's a very easy place to access as a tourist because there's a train which runs up the side of the valley. You can actually see the trace of the train here. And now I'm going to zoom in a little bit further, and you can actually see that this ice continues down, and it's down here at quite low elevations. Now, I want to establish one thing. So I've established one idea, is that ice forms in places where it never gets warm enough to completely melt. I want to bring in a little, might sound a little bit trivial, but a useful observation from the world of ecology. And that is that vegetation, like forests and crops and things, don't generally grow in places where the temperature never gets above 0 degrees C, or places where it never gets warm enough to have liquid water. Generally vegetation does not enjoy those conditions. But what I'm pointing out here is that actually there is ice which exists in this valley all the way down. In fact, you can't see it so easily, but even down to where my cursor is now, at lower elevations than lots of vegetation. Vegetation up here on the sides of this valley, much higher up here where it's colder. It's colder up here than it is down here. But yet there is ice in the bottom of this valley, and there is vegetation up on the sides of this valley. In fact, this vegetation is it's used for grazing sheep in the summer. It's a very fertile area. So hopefully you can see what I'm getting at. Ice forms at places where it never gets above 0. Yet what we're seeing is forests at the same or higher elevations than ice in this valley. Now, that's not just this one particular glacier. It's also the case in many others. That's the Argentière glacier. And that's a glacier I can't pronounce the name of in French, flowing down to elevations lower than than vegetation. Now, this might seem relatively trivial, but this is not the first time this has been noted. Right, so we've got two facts here. Ice forms at places where it never gets warm enough in the summer to melt snow. And this is a photo from Alaska, which I'm going to come back to later. Fact two is that plants can't grow in places where it never gets above zero. So this is a photo from some boreal forest where, yes, there's lots of vegetation and lots of snow, but in the summer, this place will be really warm and all the trees will do their growing when it's very warm. Yet our observation we just made is ice lies at the same elevation as forests in some places, or lower elevations. And you might see what I'm getting at here is that the thing which can explain this is that ice flows under gravity. It forms at high elevations where it's cold, but it flows downhill like a fluid, like a syrup, and flowing down through that valley down to lower elevations and can reach the same or lower elevations than vegetation of forests. Now, we've just made this inference that ice must be flowing. We weren't the first people to do that. Back in the 1800s, people like James Forbes, who was alive in the 1800s, they were debating what was going on with these weird features because it only started becoming popular to go up and as tourists to go up into the mountains and see these ice fields, and they didn't really know what was going on. And then along came James Forbes and others and argued that ice must be flowing. And look what he said. So he says, stiff and rigid as it appears, no one can doubt that it either flows or once has flowed. So he's setting up his argument here. He's saying, even if you walk on this ice, you walk on these glaciers, I should have said before, they're rock solid. If you fall over, you can hurt yourself. They can carry rocks the size of buildings. They're as hard as the rock. These glaciers are as hard as the ice in your freezer. Okay, but he's going to argue that it flows, or at least once has flowed. So it melts, it must melt. It lies on warm ground, yielding crops perhaps within 100 yards of its lower extremity. So this is just saying the same thing I just said. The ground it's on, the lower ends of the lower extremities, the ice right at the bottom of these glaciers, they're at lower elevations where it's very warm. It clearly can't just survive there all year round because it melts very rapidly in the summer when it gets warm. So then he continues, evident therefore it must be upon this ground alone that a glacier slides imperceptibly down its valley, and this independent of all direct measurements of its motion. So he's used the same inference we've said. It must be, he says, glides imperceptibly down its valley. But what he means is the same thing I was saying, flows down under its own weight, very slowly. So it's imperceptible to the naked eye, at least. It flows down valley. And then he even shows off at the end and points out that he's made this brilliant inference without any measurements of its motion. This is all independent of all direct measurements of its motion. So this is what they were arguing about in the 1800s, and they were, this was correct. This was the correct inference, because we can come back and using much more, using scientific methods, we can measure the flow of the ice. So here's an example of that. So this is a picture of me crouching or kneeling on the Antarctic ice sheet. And what we've done here is we've installed a pole, an aluminium pole in the surface, and we put a GPS receiver on the top. So GPS, Global Positioning System. It's the same, it's the way that your phone or your car's satellite navigation system knows where it is. It's the same system, except you can buy these more expensive versions which are more precise, and they can actually tell you where the instrument is to within a millimeter. Really fine resolution. So I went to this pole and many others twice, 1 year apart roughly, and measured their position 1 year and measured the position another year. And it happened that I was in a place where the ice was it was moving like all ice, which is thick enough, but it was doing it very, very slowly. And it's actually flowing about a meter a year. So you stick it in 1 year, measure where it is, come back 1 whole year later, and it's moved 1 meter. And actually that's the data shown on the right. 1 meter might not sound very dramatic, but in lots of other places it goes much faster. So you don't actually have to measure every single spot on the ice sheet with a pole, you can actually use satellites to do the same thing. So this is an animation from NASA showing the flow of the Antarctic ice sheet. Now the colors, this orange and purples, they show the speed. So I was in places which was moving about 1 meter a year, and those are all the orange locations on this map. That's the ice is moving quite slowly, only 1 meter a year. But the purples show places where it's moving more like 1,000 meters a year. So you notice that the ice, well, the other thing this map shows are all these blue lines. I'll continue the animation. You'll see that those blue lines are moving out towards the edges of the ice sheet, and they show the route that the ice takes as it flows along. So really what's going on is it's starting out in the middle, very slow in these oranges, then it's flowing down these blue lines and going into these purple areas, and it's speeding up as it goes. So overall, I'll continue the animation, but overall the ice is flowing out from the middle, out towards the edges, and getting faster as it goes. And this is ice flow. This is the thing that James Forbes was talking about. Now, I want to talk a little bit more about how the implications of that ice flow. What does it do to, what does the fact that it flows result in? One is the shape of the ice surface. This is like I said at the beginning, this is like a cross section through a big volume of ice, which is the Greenland ice sheet, the one I pointed out at the beginning. Here's a picture here, and this is like, if anyone has ever seen an MRI scan of somebody's internal organs, like maybe their brain or something, you slice through. You imagine taking a picture where you slice through there, and you see the upper surface and the bottom surface where the ice is in contact with the rock, and then all these internal structures. And they do this NASA have done this by flying around with a plane which has a radar on the mounted to the wings, sending radio waves out and listening back for the echoes, because the radio waves go partly through the ice and bounce off the rock at the bottom. So you get a picture, a sounding of all these internal structures. But we're not so interested in the internal structures today. I just want to draw your attention to this shape. Now I'm going to switch over and show you some simple math and physics which we apply to this to understand this shape. Bear with me 1 second while I switch. Now hopefully you should be able to see my screen. Okay, so I'm going to produce what's called a mathematical model. So if you haven't come across this kind of thing before, it's really just a way of applying what we've learned from our high school physics or physics classes to the real world. And the way we do that is we write down some equations which describe how things relate to each other. In my case, I'm going to be talking about how the density of the ice, the strength of gravity, the height of the surface of the ice or the thickness of the ice, and then the slope of the surface of the ice. I'm going to basically come up with an equation which relates all of those things. And then I'm going to use it to try and understand, trying to gain some intuition into what causes the ice to have this particular shape. So I'm going to draw in the first thing you do when you're making a mathematical model is draw a little cartoon to make sure we know what we're all talking about. So this brown horizontal line is the bottom of the ice, where the rock is, where the ice contacts the rock. And then this blue line is the upper surface of the ice sheet. In fact, I want to draw a little bit more generally. It could be any shape. We don't know yet. That's part of what our mathematical model is going to tell us. So that's our ice sheet. We're going to zoom in on one little location here, just this little sliver. I'm going to zoom in and bring it out over here, show you in more detail. There you go. So that's a little magnifying glass zoomed in on that one little column. So here's our bedrock surface beneath again. And then here is the surface of the ice. It's sloped. You can see that it's got a bit of a slope to it. And then I'm going to just talk about one particular column of ice within here. So hopefully everyone can see. I'll just write on here. This is the air. This is rock. and this is ice. Now, I want to draw your attention to imagine two little parcels of ice within the ice sheet, at the same height, but at different sides of our little column of ice. What you'll notice is that the one on the left has a certain amount of ice above it, but the one on the right has less ice above it. And you might have come across the idea of pressure. Pressure is the force exerted by material all around you. Like we're all experiencing air pressure right now. And if you dive to the bottom of a swimming pool, you'll experience more pressure, and that's coming from the water which surrounds you. And we're going to use that idea here because this ice and all the ice, in fact, is experiencing a pressure from the ice above it. And that is what causes the ice to flow. So let me explain that in more detail. So pressure, actually, you can express this as an equation. This is our first equation. And I'm just going to write it down and I'll explain it. So pressure is equal to the density of the ice, which has the symbol D, times by G, which is the strength of gravity, and then times by the amount of ice above you. So in the case of this little box, it's this much. In the case of this little box, it's slightly less. Okay, so H is ice above. Now, I should say this isn't just about ice, this equation. This is how you calculate pressure of any kind. So if you wanted to work out the pressure at the bottom of a swimming pool, you would just have to take the density of water, which is 1 kilogram per 1,000 kilograms per cubic meter, and the strength of gravity, which is about 10 meters per second, and then the depth of the swimming pool, and just times those three numbers together, and that will give you the pressure. So that applies in a swimming pool. It also applies in our ice. Now, we don't just want to know the pressure on this little box and this little box of ice. We want to know the pressure on the whole side of our little column of ice and how it varies with depth. And then, in fact, we also then want to compare it to how much pressure is on this side. Because ultimately what we want to do is work out how much this slope in the surface, the fact that it's higher over here than it is here, how much is that pushing the ice along? That's what's driving the ice flow. Okay, so now I'm going to have to do a little miss out some of the details because actually it uses a thing called calculus. Now, calculus is something which you'll learn at the end of high school, or if you go on to do geosciences or mathematics or physics as an undergraduate at university, you'll definitely learn more about calculus very quickly. And actually we don't use it's a really useful area of mathematics because what it allows you to do is stuff like this. So this scenario, we know the pressure at this depth. We know the pressure at this depth, and we know how the pressure varies with depth because this H is different at different depths. But what we want to know, we'll have to use calculus to work out the total amount of force on the left-hand side and the total amount of force on the right-hand side. And then we look at the difference between the two. But that's what calculus is really good for. So I'm just going to give you a flavor of it here by just writing down an equation for the total force. Let's try that again. Total force driving ice flow. So the total force driving ice flow is just going to be equal to the density again, times by gravity, times by the thickness of the ice, the total thickness. So that's this whole thing, times by the slope. The slope of the surface is just, if you were to zoom in on that upper surface, it's just like the slope of that upper surface. So like you talk about the slope of a hill when you're driving up a hill or trying to cycle up a hill, we talk about the slope of the ice surface too. So that's our equation for the total amount of force. Let me write this down over here. H is the thickness of the ice. And then slope is the surface slope. Now I'm going to take, now this is where this is what makes our model really simple here. What we're going to say is that the ice has a certain strength. So if this is the total force driving the ice flow, we're going to say that the ice has a certain strength and above which the ice will just deform. If there is a force exerted on the ice above its strength, the ice just deforms. And what we talk about scientifically, we talk about it yielding to that force. And so that actually allows us to do this. It allows us to say the strength, which is S, has to go at the top. S is strength, is equal to this. So actually, this is our model. So it's saying the strength of the ice is equal to the density of the ice times by the strength of gravity times by the thickness of the ice times by the slope. Now, you'll have to trust me on one last step to make sure that what we really want to do is come up with an equation for the thickness of the ice and compare it to our NASA data from the Greenland ice sheet. So I'm going to skip the mathematics here and just tell you the answer is the thickness H is equal to the square root of 2 times the strength divided by the density times by G times by the distance along. Distance along is X. So let's check in our heads whether this makes sense. So for one thing, density here is on the bottom of this equation. So imagine if density was, let's try gravity. Gravity is on the bottom here. So imagine if gravity was stronger. Imagine if you were on a planet which was larger, and that means the gravity was much stronger. Well, this equation says that therefore the ice thickness would be smaller. So imagine making gravity G larger, because that's on the bottom, it's dividing the right-hand side by a bigger number. That means the thickness would be smaller. So you can imagine that basically the gravity is stronger, it's pulling the ice down faster, so it's actually at a lower elevation. All right, what else? Imagine S was larger. Imagine the strength of the ice was larger. Well, in that case, because S is on the top of this equation, then H would be larger. Stronger ice is thicker. It can maintain a higher slope. And that actually is observation too. That actually fits with observations. So now the great thing about this is that we've just made a mathematical model, very, very simple, but it is nonetheless a mathematical model based on physics, which we can compare to observations. First, we can make a little plot here of what this answer actually is, because this is a very simple equation, and we can actually write down what that's going to look like just from remembering what square root graph looks like. And actually, it's going to look something like this. That's what a square root graph looks like. So that's looking pretty promising. But I'll bring you back to the PowerPoint, and then we'll do this. We'll actually compare this to the NASA data and see how well we did. Okay, hopefully we're back on the PowerPoint now. You can see our NASA data. We've got the surface slope here and the bedrock over here. And I'm going to compare it to our model. This is like a exercise that we do all the time in science. We come up with, well, we have some observations which are interesting. Well, our interesting observation is the surface has an interesting shape. Why is that? Then we come up with a simple model based on physics, which is the thing I just showed you. And then we plot out the results and compare the two. And this is what we've got. We've got distance along the horizontal axis and height of the surface along the vertical axis. And it starts out at 0, and you go 300 kilometers to the right, you go up about 250 meters. Now, actually, that's remarkably close to the observations. We start out going over to the observations now. We start out at 0 on the left, or slightly more than 0 on the left. If we move 300 kilometers to the right, see 0, 100, 200, 300, we go up about 2,500 meters. And in fact, it has a similar shape. It's steeper over here. The slope is larger over here and shallower over here. The ice is thinner over here and the ice is thicker over here. Both of those things are represented in our model. Look how it's steeper on the left, but thinner, and shallower on the right, but thicker. And actually, that is exactly what this equation shows. So as I said, there'll be people here with different experiences, different levels of familiarity with mathematics. So if this doesn't mean very much to you, don't worry. But the point I wanted to make is that imagine that the strength of the ice is the same everywhere. The density of the ice is the same everywhere. Gravity is the same everywhere. So you can only change these two things. So notice how basically if all the other things are the same and h is small, if the thickness is small, to make up for that, the slope has to be large. If you want to times those two things, those numbers together to get some constant s. If h is large over here on the right, the slope has to be small to compensate for that. So those two things compensate exactly for each other. H goes up, slope goes down. Slope goes up, h goes down. And that's really the essence of this model. It's very simple, but it really does explain some first order observations about the Greenland ice sheet. In the middle, it's thick and shallow slope. At the edges, it's steep and thin. And that's encapsulated here. So that before I finish up with an idea about how people can get more involved in glaciology, if you're interested, I wanted to just make sure everybody realizes the implications of this. So ice flow is interesting. It leads to this particular shape of the Greenland ice sheet and the shape of all other glaciers. But who cares? Why is ice flow important other than it just being interesting? But if you think about it, if our argument at the beginning is right, in these locations, the snow just falls in the winter and never melts in the summer. What if the ice never flowed? Well, then snow would continue falling here in the winter and never melting in the summer and get thicker and thicker and thicker and thicker and build up and up and up and cover the mountains. And eventually, if you include the Antarctic ice sheet in this thought experiment, then all of the oceans would just eventually be deposited as snow. All the water of the planet would be deposited as snow on glaciers and ice sheets. So that would be a bad scenario for life on this planet. But in fact, what happens is that ice flows down to lower elevations or down into the ocean, where it either melts because down in the valley here it's a lot warmer, you can tell by all the vegetation, or it breaks off into icebergs and flows away, then melts later, like it does in Antarctica or Greenland in some places. So ice flow is vitally important for the whole system. It's like a big conveyor belt, moving ice from higher elevations and far south in the South Pole down to lower elevations or down to the ocean, where it's then lost back into the ocean, and that cycle is complete. So it's a complete cycle of snow falling in the middle, ice flowing down to the edges, ice being lost back into the ocean, and then that continues. So ice float's very important for all sorts of things, including life on this planet. So before we have some time for some questions, if you're interested in any of this kind of thing, we really want to recommend a particular opportunity, which is the Juneau Icefield Research Program. See if I can show you a better video here. This is a program which happens every summer, except for unfortunately last summer, but they're back on it this year, where they bring a group of students up to this glacier in Alaska, and they ski across the glacier, cross-country skiing like the students you saw at the beginning of the video there. And they camp out on the surface of the ice, and they do sorts of experiments, and they have lectures, and they really have an incredible experience in science and adventure and field safety and team building and all these fantastic things. So these are high school students and undergraduate students, and they've been doing it for 70 years up there on the Juneau Icefield. So if you're interested in that opportunity, there's the URL at the bottom, or just search for Juneau Icefield Research Program. And it's something that me and my research group have been involved with a little bit recently and really advocating for, because we think it's a fantastic organization. So ice flows, says James Forbes and all scientists since. We use satellites, fieldwork, and mathematics and physics to understand it. If you're interested in geosciences, study at a university. It's a topic which people go to university specifically to study. But also remember to study physics, chemistry, and mathematics, because these underlying disciplines, which you might have heard more about, really are the things which we use in geosciences. And also look into opportunities like Juneau Icefield Research Program, and reach out if you have any questions, like right now or afterwards, and I'd be happy to answer them. Thanks so much for tuning in.
Fantastic. Thank you so much, Jonny. So Jonny, I'm going to have you stop sharing your screen, and our colleague from NASA. So thank you for sharing all those great NASA resources. I think that's a great segue in for Rosalba. So Rosalba from NASA has just put in a couple of links in the chat box. I see a hand in the participant list, but just so you know, we are using the Q&A box. So if you do have a questions, please type it into the Q&A box. And Rosalba, whenever you are ready, if you want to share your screen.
Thank you, Cassie. Yes, give me just 1 sec, trying to get my screen here. Can you see my PowerPoint now?
Yes, you can go ahead.
Okay, great. Okay. So, hello everyone. My name is Rosalba Giarratano. I support NASA's Office of Some Engagement at the Goddard Institute for Space Studies in New York City. And it is my pleasure to be here. I am grateful for the opportunity to share about some additional resources for exploration related to today's topic. So I did put on the chat a few links for these resources. So today I want to bring to your attention the NASA Sea Level Change Portal, the NASA Climate Site, and also the Virtual Earth System Laboratory. So the Sea Level Change Portal could be a great resource. It's a very comprehensive website where you can find descriptions of the processes causing global and regional sea level change, and also instructions as to how to connect the observing tools that are used to study them. So you will also find estimates for global mean sea level rates for 2 different periods. You're going to find them for the era of satellite observations, but yeah, I don't know when it stopped.
Okay. You can
yes,
continue.
I don't know. Yeah, so I don't know, like if you heard what I was talking about this about the sea level change portal. So just in case.
We heard most of this, yeah.
Yeah, so here, so in addition to the estimate, you can also find explanations of or technical discussions about how these estimates are calculated. So this may be helpful. The next resource is the climate site. So here you can find data from NASA's GRACE and GRACE follow-on satellites. So GRACE stands for Gravity Recovery and Climate Experiment. And so the GRACE follow-on is a mission, it's a partnership between NASA and the German Research Center for Geosciences. And it is a successor to the original GRACE mission that orbited Earth from 2002 to 2017. And so the GRACE follow-on launched in 2018 to carry on the work of GRACE while testing a new technology that is designed to improve the already pretty good precision of its measurement system. And so it will continue the work of tracking Earth's water movement to monitor changes in underground water storage and the amount of water in large lakes and rivers and ice sheets and glaciers, and sea level caused by the addition of water to the ocean. And an important thing about this is you can create an Earth data account for free so that you can access the actual data. So on my screen, I have an image of the Antarctica mass variation since 2002. But once you create your Earth data account, you can then click on where it says HTTP get data, and then you will be able to download that data. And last but not least, I also want to share with you about the Virtual Earth System Laboratory. So this is a sophisticated computer model. And so the image that you see on your screen is part of a simulation of Greenland and is the result of work carried out by the Ice Sheet System Model. That's a collaboration between NASA's Jet Propulsion Laboratory and the University of California. And so modeling teams from around the world compare their simulations against one another. And so one goal
Sorry, everybody, for the technical difficulties. Rosalba, are you able to still hear us? Okay. We will have to come back, I think, to Rosalba. In the meantime, I'd like to just open it up for questions. Should anybody have questions for Jonny about his presentation, and I will try and reshare her links here. We'll definitely be able to provide some of the links, or all of the links actually, following today's presentation. So for Jonny, while we kind of hopefully have Rosalba come back and wait for any questions. Again, to our participants here, if you do have questions, please use the Q&A box. So for Jonny, you've done several of these sessions before, and I love how you always kind of explain, kind of bring the math into all of this. And I'm just curious if you can talk about some, perhaps people always love the fieldwork aspects of your work, and hopefully you'll all be able to get back out into the field very soon. I'm curious how you might collaborate with other scientists who are working also in Antarctica and Greenland, and some of the very fun aspects of your fieldwork.
Yeah, absolutely. So that's it. I do go out of my way in these presentations to talk about the maths and physics, because I think it's an important point to make, that we use those tools that people are in some ways forced to learn as a high school student. A little bit, you learn mathematics and physics a little bit, and you may think, what's the point of this? But we do use it all the time. But we also use other tools like fieldwork and satellite observations. And fieldwork is an amazing thing to be able to do as part of your professional life. So that's a huge draw for people into geosciences too. And I really recommend it. It's an incredible experience. There are, like Cassie was like talking about, how do you collaborate with other people with fieldwork? Also, how do you join together insights you get from fieldwork and insights you get from mathematical modeling and satellite data? Those three parts of our work, which linking all three to each other is really tricky. One thing, the models we use, like for example the one you just saw, is really idealized. How do you then actually compare that in a sensible way beyond what we did today in a simple, this shape looks about right? how do we really compare simple models to observations? And there's a kind of an art to doing that, to picking out the aspects of the observations which are amenable to be tested against a simplified model. And then, of course, you have other things like satellite observations are very good. They're over vast areas of the planet. But then a field observation will, you know, really be a point measurement. And you maybe do many point measurements. So you have challenges there. And so all those things are things that people are grappling with all the time. I mean, one big collaborative project which we're involved with is the Thwaites Glacier collaboration, which involves people from the US and the UK and from Germany and Korea and many other places. And that is again, we collaborate across these different fields. People are looking at the ocean, they're looking at the atmosphere and the ice, and trying to all take measurements which are all aimed at understanding the overarching question of how ice sheets are changing over time and why. And so collaborating across disciplines is a massive challenge too, and it's something that everybody's trying to do better all the time. But there's always a tendency in all walks of life to be closed off and just talk to the people you already know. And so there's always, but everybody knows that's also not the way to make big, quick progress. So the real challenge.
I think that's a really great point. And also our viewer here, Sylvia, has written into Q&A just a thank you for this wonderful presentation. And I think being able to connect the math and top subjects we've heard of before, like calculus and math, but to glaciology, and then to connect that to the real world and how it is all connected, and you can apply it in many different ways. And we have a question here. So how much of your time do you spend outdoors versus in the lab? I think this is a really great question, and one that a lot of our scientists also get.
Well, much more time in the lab, much more time in front of a computer, really. Even the people who really are dedicated to field work, and they might go on field trips every year or maybe twice a year, and each one of them might be up to 2 months. So the people who do the most proportion of their year in the field are probably doing 3 months or 4 months per year, which sounds is a lot, right? Especially if you like hanging around with your family. But it's still proportionally, you're still more time in front of a computer. So I don't know, unfortunately or fortunately for anybody looking to a career in geosciences, it will always be the majority of your time is in front of a computer and in an office or in a lab. But now and again, you do field work. The minority of time is in the field, and that can have an outsized impact on your life because it's an incredible experience and you learn a lot and all sorts of other good stuff. But for me personally, more like a few weeks every couple of years at the moment. It was more in the past.
Yeah. Well, thank you for that and for the questions. So Rosalba has reshared the links, and we'll definitely be sure to share the resources. This video will get posted. You can continue to tune in. You can tune in again, and it'll be on the website as well as YouTube. And I'll definitely share the recording. Jonny, any last words before we wrap up here today?
No, thank you for coming along, everyone. Thanks for showing an interest and just emphasize that physics side of things. Encouraging your if you're a student, or encouraging your students to do physics is always the thing I think is the top line headline.
Fantastic.
Part of these.
Awesome. Thank you so much. So thank you again, everybody, for tuning in. Hope you have a great rest of your day. And thank you again, Jonny. We'll see you soon, hopefully. Bye, everybody. Thank you.